4 bridges, 1 river, and a walk nobody could finish. That old puzzle started a whole branch of mathematics. In this chapter we learn its language. Welcome to graphs. Hello and welcome. Let's start this chapter together. It is about graphs. A graph is an easy idea. We draw some dots. We call each dot a vertex. Then we join some dots with lines. We call each line an edge. That is all a graph is. With this simple idea, we can model many real things. We can model a computer network. We can model roads in a city. We can model friends on the internet. Take your time. Each idea builds on the one before it. This is the plan for the whole chapter. First, graphs and graph models. Then the words we use, and some special kinds of graphs. Next, how to store a graph in a computer, and how to check if 2 graphs are really the same. After that, connectivity. It asks whether we can travel between the dots. Then Euler and Hamiltonian graphs. Shortest path problems are in the book, but not in these slides. Planar graphs are in the book only as well. And graph coloring too. Let's begin with the first one. Now we turn to the first topic. It is graphs and graph models. We learn what a graph is, the different kinds of graphs, and how to use a graph to model a real problem. This is the plan for this section. First, we meet the idea of a graph. Then we learn the family of graph types and how they differ. At the end, we use graphs to model real networks. Let's start. Let's look at the definition. A graph has 2 parts. The first part is a set of dots called vertices. The second part is a set of lines called edges. Every edge joins its endpoints. So to write a graph down, we need 2 lists, 1 list of dots and 1 list of joined pairs. On the next slide, we read one off a picture. Let's read this picture, the way we will read every picture in this chapter. Step 1, count the dots. There are 4, a B, C, and D. Step 2, look at the lines. Do they carry arrows? No, so this graph is undirected. Step 3, list the joined pairs. On B, A, and C, B, and C, B, and D, C, and D. Step 4, count them. There are 5 lines, so this graph has 4 vertices and 5 edges. Now we know everything about it. One warning before we go on. These are not the graphs of functions from chapter 2. That is a different meaning of the same word. Now the idea that matters most. Only the connections matter. It does not matter how long a line is. It does not matter if 2 lines cross. It does not matter where we put a dot. 2 drawings that join the same dots are the same graph. And we study only finite graphs. That means a graph with a limited number of dots. 4 new words now. A simple graph is the plainest kind. Each line joins 2 different dots, and no 2 lines join the same pair of dots. A multigraph is different. It may have 2 or more lines joining the same pair of dots. If M lines join U and V, we say the edge UV has multiplicity M. That just means how many copies there are. A loop is a line that starts and ends at the same dot. A pseudograph is the most general kind. It may have loops, and it may have multiple edges. One warning. Different books use different words for these ideas, so always check the words first. Let's classify this graph, one question at a time. Question 1. Do the lines carry arrows? No, so the graph is undirected. Question 2. Is there a line from a dot back to itself? Yes, there are 2. One at B and one at C. Each of those is a loop. Question 3. Is any pair of dots joined by more than one line? Yes. Look at B and see two lines join them, so the edge BC has multiplicity 2. Question 4, put the answers together. This graph has loops and it has multiple edges. Only one type allows both. It is a pseudograph. Now we add direction. In a directed graph, every line has an arrow. The arrow tells us the way to travel. We write the edge as an ordered pair. U then V, this edge starts at U and ends at V. Order matters here. The edge from U to V is not the same as the edge from V to U. If the lines have no arrows, we call the graph undirected. That is the kind we saw before. Two more kinds of directed graph. A simple directed graph is the plainest. It has no loops and no multiple edges. A directed multigraph is more general. It may have 2 or more arrows from one dot to another. When M arrows run from U to V, we say the pair UV has multiplicity M. Now a point that catches people out. Suppose one arrow goes from B to C, and another arrow goes from C to B. Those are not multiple edges. They are two different ordered pairs. Multiple edges means two arrows the same way, from the same start to the same end. For that to work, we must relax one thing. In a plain directed graph, the edges form a set, and a set holds each ordered pair only once. In a multigraph, they form a multiset instead, so the same pair can appear as many times as there are arrows. Let's read this directed graph. Step 1, count the dots, 3 of B and C. Step 2, list the arrows as ordered pairs. A to B, A to C, B to C, and C to B. Step 3, is there a loop, an arrow from a dot to itself? No. Step 4, is any ordered pair listed twice? No. The pair BC and the pair CB look similar, but they are different pairs because the order is different. So nothing repeats, and this is a simple directed graph. Now the same reading on a busier picture. Step 1. Look at the pair A to B. How many arrows run that way? Just one, so its multiplicity is 1. Step 2. Look at the pair B to C. 2 arrows run that way, both from B to C, so its multiplicity is 2. Step 3. Are there loops? Yes, there is a loop at B and a loop at C. Step 4. Arrows repeated in the same direction plus loops. That makes this a directed multigraph. Now we use graphs to model a real thing. We model computer networks. In every model here, a dot is a data center, and a line is a communication link between two data centers. The first question is simple. Do we only want to know if two data centers are joined, yes or no? Do all links work in both directions? Do we not care how many links there are? If the answer to all three is yes, then a simple graph is the right choice. We see one here, with data centers in 7 cities. Now we change the question. Do we care how many links join two data centers? If we do, then one line is not enough. We draw one line for each link. Look at San Francisco and Denver. 2 lines run between them, so there are 2 links. Denver and Chicago also have 2. A graph that allows this is a multigraph. Now we change the question again. Does a data center have a diagnostic link to itself, one it uses to test its own equipment? If it does, we need a line from a dot back to the same dot. That is a loop. Look at San Francisco, Los Angeles, Denver, and Detroit. Each has a small loop. A graph that allows both loops and multiple edges is a pseudograph. Now the last change. Are the links one way? Then each line needs an arrow, And if there can be several one-way links between the same two data centers, we need repeats as well. That gives a directed multigraph. Look at Los Angeles and Denver. One arrow runs from Los Angeles to Denver, and nothing comes back. If we only wanted to know whether at least one link runs each way, a plain directed graph would be enough. Before we look at the table of types, learn these 3 questions. They fix the type every time. Question 1. Are the lines undirected with no arrows or directed with arrows or a mix of both? Question 2. Are there multiple edges, that is, 2 or more lines between the same pair of dots? Question 3. Are there loops, that is, lines from a dot to itself? Answer those 3 and the type follows. This table sums up all the types. The 3 columns are the 3 questions. Are the edges directed? Are multiple edges allowed? And are loops allowed? A simple graph is undirected, with no multiple edges and no loops. A multigraph is undirected and allows multiple edges, but no loops. A pseudograph is undirected and allows both. A simple directed graph has arrows, but no multiple edges and no loops. A directed multigraph has arrows and allows both. And a mixed graph even allows arrows and plain lines together. Graphs appear almost everywhere. Look at how many different systems they model. Social networks, where the dots are people. Communication networks, where the dots are machines. Information networks, like the pages of the web. Software design, where the dots are parts of a program. Transportation networks, like roads and flights. And biological networks, like proteins in a cell. It really is very hard to find a field where graph theory has no use, so a small challenge for you. Can you think of one area with no application of graphs? Let's look at social networks. A social network is a picture of people and how they relate. Each dot stands for one person or one group. Each line stands for a relationship between them. We use 3 main kinds of graph here. The first kind is a friendship graph. It is undirected, so the lines have no arrows. We join 2 people if they are friends. The second kind is a collaboration graph. It is also undirected. We join 2 people if they work together in some way. The third kind is an influence graph. It is directed. We draw an arrow from one person to a second person if the first person can influence the second. So the direction of the arrow carries the meaning. This is a friendship graph. Each dot is a person. Each line joins 2 Facebook friends. The lines have no arrows, and there is a good reason for that. If Paula is a friend of Todd, then Todd is a friend of Paula. The relationship works both ways. Look at Liz. She has lines to Leela, Paula, Amy, Todd, and Steve. Those 5 are her friends. Now look at Kyrie out at the bottom. She has only one line to Joel. This is an influence graph. Now the lines have arrows. An arrow from Brian to Fred means Brian can influence Fred. The arrow points only one way. Brian may influence Fred, but that does not mean Fred can influence Brian. So this graph is directed. Look at the arrow that goes from Deborah up to Linda. It tells us Deborah can influence Linda and nothing more. Brian has 3 arrows leaving him, to Deborah, to Fred, and to Yvonne. So Brian influences 3 people. Now we look at collaboration graphs. In a collaboration graph, we join 2 people when they work together in a set way. The first example is the Hollywood graph. It models how film actors work together. Each dot is an actor. We draw a line between two actors if they acted in the same movie. Acting together works both ways, so the lines have no arrows. Later, in section 10.4, we use this graph to define Kevin Bacon numbers. The second example is an academic collaboration graph. It models researchers who write papers together. Each dot is a researcher in some field. We join two researchers with a line if they wrote a paper together, as co-authors. Writing together also works both ways, so again the graph is undirected. Later we use this graph for mathematicians to define what are called Erdős numbers. Next we look at information networks. These graphs link pieces of information. The first example is the web graph. Each dot is a web page. Each arrow is a link from one page to another page. The arrows have a direction because a link points one way. Page A may link to page B, but page B need not link back. The second example is a citation network. Each dot is a research paper. We draw an arrow from one paper to a second paper when the first paper cites the second one as a reference. This graph is directed too. Now we turn to transportation. Graphs help us study how people and goods move. The first example is an airline network. Each dot is an airport. Each arrow is one flight. The arrow starts at the departure airport and ends at the arrival airport. We use a directed multigraph here. It is directed because a flight goes one way. It is a multigraph because there can be many flights between the same two airports, and each flight is its own arrow. The second example is a road network. Each dot is an intersection. Each line is a road. A two-way road is an undirected edge with no arrow. A one-way road is a directed edge with an arrow that shows the allowed direction. Now we look at software design. When we build a program from the top down, we split it into modules. Each module does one job. A module dependency graph shows how these modules rely on each other. Each dot is a module. We draw an arrow from one module to a second module when the first module depends on the second. So the arrow points from a module to the thing it needs. We must understand these arrows before we write any single line of code. This is the dependency graph for a web browser with 7 modules. The module called main sits at the top. 4 arrows leave it, so main depends on the display module, the parser, the protocol module, and the abstract syntax tree. Follow the parser next. 2 arrows leave it, so the parser depends on the abstract syntax tree and on the page module, and the protocol module depends on the page and the network modules. Now read the arrows backwards, and you have the build order. A module can only be finished after everything it points to is finished. A second software model now, called a precedence graph. It tells us the order in which statements must run. Each dot is one statement in the program. We draw an arrow from one statement to a second statement when the second statement cannot run before the first. So the arrows are the rules about order. Let's look at a small program and work out its arrows. The table has 3 columns. The statement, what it does, and the values it reads. That last column is the key to everything. Statement 1 sets it to 0, and it reads nothing. Statement 2 sets B to 1, and it also reads nothing. Statement 3 sets C to +1, so it reads A. Statement 4 sets D to B plus A, so it reads B and A. Statement 5 sets E to D plus 1, so it reads D. And statement 6 sets F to C plus D, So it reads C and D. Notice that no two statements write the same variable, so the only thing that fixes the order is reading. A statement must wait for whatever produces the values it reads. Let's build the arrows, one statement at a time. Step 1. Statement 3 reads A who writes A. Statement 1. So statement 1 must run first. We draw an arrow from S1 to S3. Step 2. Statement 4 reads and B. Statement 1 writes A, and statement 2 writes B, so we need two arrows into S4, one from S1 and one from S2. Step 3. Statement 5 reads D. Statement 4 writes D, so we draw an arrow from S4 to S5. Step 4. Statement 6 reads C and D. Statement 3 writes C, and statement 4 writes D, so two arrows go into S6, one from S3 and one from S4. That is 6 arrows in all, and the picture beside the table shows every one of them. Now we look at biology. The first example comes from ecology. It is called a niche overlap graph. Each dot is a species. We join two species with a line when they compete for the same food. This graph is undirected, and here is why. If the hawk and the owl compete for food, then the owl and the hawk compete too. The relationship works both ways, so the line needs no arrow. This is the niche overlap graph for a forest. We see 9 species: the raccoon, the hawk, the owl, the opossum, the squirrel, the crow, the shrew, the mouse, and the woodpecker. A line between 2 of them means they hunt or eat the same food. Look at the squirrel. It has lines to the raccoon, the hawk, the owl, the crow, and the opossum, so the squirrel competes with 5 other species. Now look at the shrew. It has only 2 lines to the mouse and to the woodpecker, so the graph shows us exactly who competes with whom. The second biology example comes from molecular biology. We can model how proteins meet and act in a cell. This is called a protein interaction network. Each dot is one protein. We join 2 proteins with a line if they interact. This graph is undirected. These graphs can be very large. One graph can have more than 100,000 proteins and more than 1 million edges. Because they are so big, we often cut them into smaller pieces, called modules. Each module holds the proteins for one job in the cell. The picture shows one module of a protein interaction graph. These proteins work together to break down RNA in a human cell. Each dot is one protein, and each line means those 2 proteins interact. Even this small piece of the whole graph is already busy. Now imagine 100,000 dots. That is why we study the graph one module at a time. Now we turn to the second topic. It is about the words we use for graphs and some special families of graphs. We learn when 2 vertices are neighbors. We learn the degree of a vertex, and we study 2 important rules about degrees. This is the plan for this section. First, we cover the basic terms. Then we look at some special types of graphs. Next come bipartite graphs, and how bipartite graphs are used for matching. Some real applications of the special types are in the book, but not in these slides. And at the end, we build new graphs from old ones. Let's learn the basic words. 2 vertices are adjacent when an edge joins them. We also call them neighbors. That edge is incident with both vertices. We also say the edge connects them. Next comes the neighborhood. The neighborhood of a vertex V is the set of all its neighbors. We write it as n of V. If it was a set of vertices, Then n of A is the set of all vertices that are neighbors of at least one vertex in A in symbols. N of A is the union, over every vertex V in A, of n of V. Now the degree. The degree of a vertex is how many edges touch it. We write it as deg of V. There is one special rule, and it catches people out every time. A loop is an edge from a vertex back to itself. It touches that vertex at both of its ends. So a loop counts as 2, not 1. Remember that rule for the next few slides. Before we count anything, let's read the picture. Step 1, count the dots. There are 7 named through G. Step 2, look at the lines. No arrows and no line loops back to its own dot. Step 3, count the lines. There are 9. A B, a F, B, C, B, F, B, E, C, F, C, E, C, D, and F, E. Step 4, one dot stands alone. Vertex G has no line at all. Remember that because its degree will be 0. Now we take the vertices one at a time and list the edges that touch each one. Vertex A 2 edges touch it, a B and a F, so its degree is 2. Vertex B 4 edges, a B, B, C, B, F, and B, E degree 4. Vertex C 4 edges, B, C, C, F, C, E, and C, D degree 4. Vertex D only one edge, C, D degree 1. Vertex E 3 edges, B, E, C, E, and F, E degree 3. Vertex F 4 edges, a F, B, F, C, F, and F, E degree 4. And vertex G no edge touches it at all, degree 0. This is a check you should always run. Every edge has 2 ends. So when we add up all the degrees, each edge gets counted twice. That means the total must be twice the number of edges. Line 1 is what we want to work out, the sum of the degrees. Step 1. Light the 7 degrees in order, 2, 4, 4, 1, 3, 4, and 0. Step 2. Add them. 2 plus 4 is 6, plus 4 is 10, plus 1 is 11, plus 3 is 14, plus 4 is 18, plus 0 is still 18. Step 3. Is 18 twice the number of edges? The graph has 9 edges and 2 times 9 is 18. It checks out. If it had not, we would have miscounted somewhere. The neighborhood is easy once we have the edges. For each vertex, we walk along every edge that touches it and write down the vertex at the far end. The neighbors of our B and F2 of them. The neighbors of B are a C, E, and F4. The neighbors of C are B, D, E, and F4. The only neighbor of D is C. The neighbors of E are B, C, and F3. The neighbors of F are a B, C, and E4. And G has no neighbor at all, so its neighborhood is the empty set. Look at the last column. In this graph, the size of the neighborhood matches the degree every time. That happens because there are no loops and no multiple edges here. On the next graph, it will not. Let's read this one carefully, because it is not a simple graph. Step 1, count the dots. 5, a B, C, D, and E. Step 2, look for loops. There is one at vertex B. Remember, that loop will count as 2. Step 3, look for repeated lines. 2 lines join and E3 lines join D and E. Step 4, count every line. 1 a B, 1 B C, the loop at B, 1 a D, 1 B E, 1 B D, 2 a E, and 3 D E1 plus 1 plus 1 plus 1 plus 1 plus 1 plus 2 plus 3 is 11 edges. Now the degrees. For each vertex we count edge ends, not lines. So a loop counts twice, and a repeated line counts once for each copy. Vertex A 1 edge to B, 1 to D, and 2 to E1 plus 1 plus 2 is 4. Vertex B 1 edge to I, 1 to C, 1 to E, 1 to D, and then the loop, which counts as 2. 1 plus 1 plus 1 plus 1 plus 2 is 6. Vertex C just one edge to B degree 1. Vertex D 1 edge to A, 1 to B, and 3 to E1 plus 1 plus 3 is 5. Vertex E1 edge to B, 2 to A, and 3 to D1 plus 2 plus 3 is 6. Now the check. 4 plus 6 plus 1 plus 5 plus 6 is 22, and twice 11 edges is also 22. The count is right. Now the neighborhoods. A neighborhood is a set of names, so each name appears once, however many lines run to it. The neighbors of our B, D, and E3 names, even though it has degree 4, because 2 of its edges both go to E. The neighbors of B are a B, C, D, and E. Look at that list again. B is in its own neighborhood. That is the loop. The only neighbor of C is B. The neighbors of D are a B and E. And the neighbors of E are a B and D. So this is the lesson. In a simple graph, the size of the neighborhood equals the degree. Once loops or repeated edges appear, that stops being true. A very useful rule now. It is called the Handshaking theorem. It says that 2 times m equals the sum of all the degrees. Here m is the number of edges, and the sum runs over every vertex in the graph. We already used this as a check twice. Now we say why it is true. A nice picture helps. Imagine people at a party. Draw an edge each time 2 people shake hands. Then the degree of a person is how many hands that person shook. Every handshake involves 2 hands. So the total of all the counts is twice the number of handshakes. Let's prove it in 3 steps. Line 1 is the thing we want to understand, the sum of all the degrees. Step 1. What does the degree of V actually count? It counts the edge ends sitting at V, so adding the degrees over all vertices counts every edge end in the graph, exactly once. Step 2. Now count the same ends a different way. Go edge by edge. Every edge has exactly 2 ends, so the number of ends is 2 times the number of edges. A loop is no exception, and that is exactly why a loop counts 2. Step 3. The number of edges is m, so the total is 2m. Both ways of counting must agree, and the theorem is proved. Let's use the rule to count edges. Line 1. Start from the sum of the degrees, because that is the side we can work out from the question. Step 1. There are 10 vertices, and each one has degree 6, so the sum is 6 times 10. Step 2. 6 times 10 is 60. Step 3. The handshaking theorem says this same sum equals 2m. Step 4. So 2m is 60. Divide both sides by 2 and m is 30. The graph has 30 edges. Now a question with a surprising answer. Line 1. Again we start from the sum of the degrees. Step 1. 5 vertices, each of degree 3. So the sum is 3 times 5. Step 2. 3 times 5 is 15. Look at that number. 15 is odd. Step 3. But the handshaking theorem says the sum must equal 2m 2 times any whole number is even. An odd number can never equal an even number. So no such graph exists. Notice what we did. We did not search for the graph and fail. We proved it cannot be built. Another rule about degrees. It says the number of odd degree vertices is always even. Let's prove it. First, split the vertices into 2 groups. Group V1 holds the vertices of even degree. Group V2 holds the vertices of odd degree. Line 1. Start from 2m, whatever m is, 2m is even. Step 1. The handshaking theorem says 2m equals the sum of all the degrees. Step 2. Split that sum into the two groups, 1 piece over v1, 1 piece over v2. Step 3. The piece over v1 is a sum of even numbers, so it is even. The whole thing is even. Take an even number away from an even number and you get an even number. So the piece over v2 must be even too. And now the last move. That second piece adds up odd numbers. When do odd numbers add to an even total? Only when there is an even count of them. 2 odds make an even. 3 odds make an odd. So v2 has an even size and we are done. Now we look at directed graphs again. Take the edge uv, it starts at u, and it ends at v. We say u is the initial vertex, and v is the terminal vertex. We also say u is adjacent to v, and v is adjacent from u. Those two phrases sound alike, so read them slowly. Adjacent to points forward along the arrow, adjacent from points backward. And for a loop, the start and the end are the same vertex. Now we count directions. The in-degree of a vertex is how many arrows point into it. We write it deg minus of v, and the minus sign reminds us the arrow is coming in. The out-degree is how many arrows leave it. We write it deg plus of v. And the loop rule again in its new form. A loop starts at the vertex and ends at the same vertex, so it adds 1 to the in-degree and 1 to the out-degree, not 2 to either. Let's read this directed graph before we count anything. Step 1. 6 dots are through F, and every line carries an arrow. Step 2. Look for loops. There are 3 at C and at E. Step 3. Count the arrows. The 3 loops then are to C, are to B, C to B, are to E, E to A, B to D, D to C, D to E, and E to D. That is 12 arrows. Step 4. And vertex F sits alone, with nothing pointing in and nothing pointing out. Now the in-degrees. For each vertex we look only at arrows whose head lands there. Vertex A, the loop at A ends at A, and the arrow from E ends at A in degree 2. Vertex B, 2 arrows land there, 1 from A and 1 from C in degree 2. Vertex C, 3 land there, the loop at C, the arrow from A, and the arrow from D in degree 3. Vertex D, 2 land there, from B, and from E in degree 2. Vertex E3 land there, the loop at E, the arrow from A, and the arrow from D in degree 3. And vertex F, nothing points at it, in degree 0. Now the out degrees. Same graph, but this time we look only at arrows whose tail sits at the vertex. Vertex A, the loop starts there, and 3 more arrows leave to B to C, and to E out degree 4. Vertex B, only 1 arrow leaves, to D out degree 1. Vertex C, the loop, and 1 arrow to B out degree 2. Vertex D, 2 leave, to C and to E out degree 2. Vertex E, the loop, and 2 more, to and to D out degree 3. And F again has nothing, out degree 0. A rule for directed graphs now, and our own numbers will confirm it. Line 1. Take the sum of the in-degrees. Step 1. Add the in-degrees we just found, 2, 2, 3, 2, 3, and 0. That is 12. Step 2. Now add the out-degrees, 4, 1, 2, 2, 3, and 0. That is also 12. Step 3. And the graph has 12 edges. Why must this always happen? Look at 1 arrow. It has exactly 1 head where it points. That adds 1 to somebody's in-degree. It has exactly 1 tail where it starts. That adds 1 to somebody's out-degree. so each sum counts every edge exactly once. Now some special simple graphs that come up again and again. The first one is the complete graph. A complete graph on n vertices is written as Km in a complete graph. Every pair of different vertices is joined by exactly one edge, so every vertex touches every other vertex. You see K1 up to K6 along this row. K1 is just a single dot with no edge. K2 has two vertices and one edge. K3 is a triangle. K4, K5, and K6 add more vertices, and each new vertex connects to all the others. Let's count the edges of Kn using the handshaking theorem. Line 1. Pick any vertex v of Kn and ask for its degree. Step 1. In a complete graph, v is joined to every other vertex. There are n vertices in all, and v is not joined to itself, so its degree is n-1. Step 2. Every vertex has that same degree, so the sum of the degrees is n times n-1. Step 3. The handshaking theorem says that sum is 2m. Step 4. Divide both sides by 2. So m is n times n-1 over 2. That is also the binomial coefficient n choose 2, which makes sense because an edge is just a choice of two vertices. Try it on K4. 4 times 3 over 2 is 6 edges, and you can count 6 in the picture. The next family is the cycle. A cycle Cn for n at least 3 is a ring of n vertices. We join vertex 1 to vertex 2, vertex 2 to vertex 3, and so on, and then we join the last vertex back to the first, so it forms a closed loop. You see C3 first, which is a triangle. Then C4, which is a square. Then C5 and C6, with 5 and 6 vertices in the ring. Count the edges with the handshaking theorem. Every vertex has exactly 2 neighbors, so the degrees add to 2n, and the number of edges is n. The next family is the wheel. A wheel Wn starts from a cycle C, and then we add one new vertex in the middle, and we join this middle vertex to every vertex on the cycle. It looks like a wheel with spokes. You see W3 up to W6 here, each one a ring with a hub in the center. Count the edges again with degrees. The hub in the middle is joined to all n rim vertices, so its degree is n. Each rim vertex has its 2 cycle neighbors plus the hub, so its degree is 3. The degrees add to n plus 3n, which is 4n, and half of that is 2n edges. This family is called the n cube. Written as Qn, each vertex is a bit string of length, and so Qn has 2 to the power n vertices. We put an edge between 2 vertices when their bit strings differ in exactly 1 bit. Look at Q1. It has 2 vertices, 0 and 1. They differ in 1 bit, so they share an edge. Q2 has 4 vertices, 0, 0, 0, 1, 1, 1, and 1, 0. They form a square. Walk around it, and each step flips exactly 1 bit. Q3 has 8 vertices, and it looks like a cube. In Q3, the vertices 0, 0, 0, and 1, 0, 0 differ only in the first bit, so they are joined. Special graphs also help us build computer networks. These are the 3 most common shapes. Picture is a star. All the devices connect to one central device, drawn here in yellow. Picture B is a ring. Each device connects to exactly 2 neighbors, and a message travels around the ring. And picture C mixes the 2. Every device sits on a ring, and every device also reaches the hub in the middle. Now let's name each shape, using the families we just learned. The star is the complete bipartite graph, K1, in one vertex on one side, n vertices on the other, and every pair joined. The ring is the cycle Cn. And the star plus ring together is exactly the wheel Wn, a cycle with a hub joined to every rim vertex. So 3 familiar families turn up as 3 real network designs. For parallel processing, many processors must talk to each other, because one processor may need results from another. So we need a wiring plan, and a graph is exactly that plan. The N-cube-Qn is one common choice, used for example in the Intel Hypercube. Another common choice is the mesh network. In a mesh, we lay the processors out in a grid. Each processor is named Pi, j by its row and its column, and it links to the processors directly next to it. Let's look at one. This is a mesh for 16 processors, laid out as a 4x4 grid. Read one name. P1, 2 sits in row 1 in column 2. Now look at its lines. It joins P0, 2 above, P2, 2 below, P1, 1 on the left, and P1, 3 on the right. 4 neighbors. A processor on the edge of the grid has 3 neighbors, and one in a corner has only 2. So the degrees are not all the same, and that matters when you plan how work moves through the machine. Now we meet an important type, the bipartite graph. A simple graph G is bipartite if we can split its vertices into 2 groups, V1 and V2. The 2 groups share no vertex, and every edge must go from one group to the other group. No edge is allowed inside the same group. An easier way to think about it. Try to color each vertex red or blue so that no edge joins 2 vertices of the same color. If you can do this, the graph is bipartite, and the red vertices are one group and the blue vertices are the other. Let's test this graph, one step at a time. Step 1, we propose a split. Put a B and D in the first part. They are drawn red. Step 2, put C, E, F, and G in the second part. They are drawn blue. Step 3, now check every edge. A goes to G, F, and E all blue. B goes to G, E, and C all blue. D goes to F, C, and G all blue. Step 4, so no edge joins 2 reds and no edge joins 2 blues. The split works and G is bipartite. Now let's try the same on a graph where it fails. Step 1, start anywhere. Color a red. That is a free choice because swapping all the colors changes nothing. Step 2, every neighbor of a must now be blue. The neighbors of our B, D, E, and F, so all 4 are blue. Step 3, now look at B and F, both are blue. Is there an edge between them? Yes, there is. So we have an edge joining 2 vertices of the same color. Step 4, and we were forced into it. There was no other choice after step 1, so no valid coloring exists, and H is not bipartite. Let's test the 6th cycle. Step 1, color V1 red, then walk around the ring in alternate, red, blue, and so on. Step 2, the odd-numbered vertices come out red. That is V1, V3, and V5. Step 3, the even-numbered vertices come out blue. That is V2, V4, and V6. Step 4, now the important check. The last edge closes the ring from V6 back to V1. V6 is blue and V1 is red. Different colors, so it is fine. Every edge joins a red to a blue, so C6 is bipartite. Now the 3 cycle, and this time the answer is no. Step 1, we must split 3 vertices into 2 non-empty groups. Whatever we try, one group ends up with two of them. There is no way around that. Step 2. In C3, every vertex is joined to every other vertex. It is a triangle. Step 3. So those two vertices sitting in the same group are joined by an edge. That is exactly what bipartite forbids. Step 4. So C3 is not bipartite. And this is the general rule behind both examples. Alternating colors around a ring works only if the ring closes on a different color. That happens exactly when n is even. So an even cycle is bipartite, and an odd cycle is not. Now we join two ideas, complete and bipartite. A complete bipartite graph is written Km, and we split the vertices into two groups. The first group has m vertices, and the second group has n vertices. Then we draw an edge from every vertex in the first group to every vertex in the second group. So the two groups are joined in every possible way, but nothing inside a group is joined. The first picture is K2, 3, two vertices on one side, 3 on the other. Then K3, 3, K3, 5, and K2, 6. Counting the edges is easy. Each of the m vertices sends out n edges, so there are m times n edges in all. We can also build new graphs from old ones. First, a subgraph. A subgraph of a graph G takes some of the vertices, and some of the edges of G. The vertex set W sits inside V, the edge set F sits inside E. If the subgraph is not the whole graph, we call it a proper subgraph. Look at the example. The first picture is K5, the complete graph on 5 vertices. Beside it is a subgraph. It keeps only 4 of the 5 vertices, because vertex D has been dropped. And among those 4 vertices, K5 had 6 edges, but the subgraph keeps only 5 of them. The edge from C to E is gone. Second, the induced subgraph. Here we pick a set W of vertices. Then we keep every edge of G that has both of its endpoints inside W. We are not allowed to drop any of them. The second picture is the subgraph of K5 induced by the set of B, C, E. All 6 edges between those 4 vertices are kept, so it is the complete graph K4. Now compare the two slides. A plain subgraph may drop edges. An induced subgraph must keep every edge that fits inside the chosen vertices. The vertices decide everything. A real use of bipartite graphs now, matching. We match the members of one set to the members of another set. Take job assignments. One group of vertices is the employees. The other group is the jobs. We draw an edge from an employee to each job they are trained to do. Take marriage. One group is the men, the other group is the women, and an edge joins 2 people who are acceptable spouses. In both cases, we want a matching. A matching is a set of edges chosen so that no person is used twice, and no job is used twice. This is the first picture. The top row holds 4 employees, Alvarez, Berkovitz, Chen, and Davis. The bottom row holds 4 jobs, requirements, architecture, implementation, and testing. A line means that employee is trained to do that job. Read one row. Berkovitz has 3 lines, so Berkovitz can do requirements, architecture, or implementation. Now read Davis. Davis has only 1 line to implementation. That single line will matter, because if we want everyone working, Davis must get implementation. This is a matching for a second team. Washington takes architecture, Chuan takes requirements, Ibarra takes testing, and Ziegler takes implementation. Now check that this really is a matching. Count the edges, 4. Does any person appear on 2 edges? Number, does any job appear on 2 edges? No. So nobody is double booked and no job is done twice. And because all 4 jobs are covered, this matching is as large as it could possibly be. One more way to build a new graph is the union. Take 2 simple graphs, G1 and G2. The union has all the vertices of both graphs and all the edges of both graphs. Look at the example. G1 uses the vertices of B, C, D, and E. G2 uses a B, C, D, and F. So the union has 6 vertices of B, C, D, E, and F, and every edge from either graph is kept. G1 had 6 edges. G2 had 5. 2 of them, a B and BC, appear in both, and we keep only 1 copy of each. So the union has 9 edges. Vertex E came only from G1, and vertex F came only from G2, but both are in the union. Now we turn to a new topic. It is about how we store a graph and how we compare 2 graphs. So far we have drawn graphs as pictures, but a computer cannot read a picture. It needs numbers and lists. This is the plan for this section. First, we learn adjacency lists. That is a simple list of neighbors. Then adjacency matrices. That is a grid of zeros and ones. Then incidence matrices. This grid links vertices to edges. And last, we learn when 2 graphs are isomorphic. That means they are the same graph, just drawn in a different way. Let's look at adjacency lists. An adjacency list is short and simple. We make 1 row for each vertex. In that row, we write the vertices next to it. Nothing else is stored. That is why this way is good for a graph with few edges. We only write down the connections that really exist. Notice the small condition in the definition. The graph must have no multiple edges, because a plain list of names cannot say how many lines there are. Let's build the list for this graph, 1 vertex at a time. Vertex A, walk out along every line from A we reach B, C, and E, so the row for it is B, C, E. Vertex B, only 1 line leaves B, and it goes to A, so the row for B is just A. Vertex C, from C we reach a D and E. Vertex D, from D we reach C and E. Vertex E, from E we reach a C and D, now a useful check. Each edge shows up twice in the whole list, once from each end. Count the names. 3 plus 1 plus 3 plus 2 plus 3 is 12, and the graph has 6 edges. 12 is 2 times 6, exactly as the handshaking theorem promised. Now the same idea for a directed graph. The rows change meaning. Each row is a start vertex, and it lists everywhere we can reach in 1 step, following the arrows. From A we can reach B, C, D, and E. From B we can reach B itself, because of the loop, and also D. From C we can reach A, C again by its own loop, and E. From D we can reach nothing at all. No arrow leaves D, so its row is empty. That empty row is real information, so we still write the row. And from E we can reach B, C, and D. Count the names this time. 4 plus 2 plus 3 plus 0 plus 3 is 12, and the graph has 12 arrows. For a directed graph, each arrow appears exactly once, not twice. Now we meet the adjacency matrix. First we put the vertices in some order. We call them V1, V2, up to Vn, then we build a square grid with n rows and n columns. We call each entry a sub ij. The rule is easy. The entry a sub ij is 1 if vertex vi and vertex vj share an edge. The entry is 0 if they do not. So everyone means these two are joined, and every zero means they are not. The order of the vertices is your choice, but you must use the same order down the rows and across the columns, or the matrix means nothing. Let's fill this matrix in, one row at a time. We use the order of B, C, D. Row A is adjoined to itself. No, so the first entry is 0 to B, yes 1 to C, yes 1 to D, yes 1. So the row is 0, 1, 1, 1. Row B to a yes 1, to itself 0, to C yes 1, to D no 0, so 1, 0, 1, 0. Row C to a 1, to B 1, to itself 0, to D no, so 1, 1, 0, 0. Row D to a 1, to B no, to C no, to itself 0. So 1, 0, 0, 0. Now look at the whole grid, folded along the top left to bottom right diagonal. The two halves match. That is because the graph is undirected. A second graph now, again with the order of B, C, D. This one is a 4-cycle drawn as a square. Row A is joined to B and to C and to nothing else. So 0, 1, 1, 0. Row BB is joined to and to D, so 1, 0, 0, 1. Row CC is joined to and to D, so 1, 0, 0, 1. Row DD is joined to B and to C, so 0, 1, 1, 0. Every row here has exactly 2 ones. That tells us every vertex has degree 2, which is what we expect from a cycle. 2 useful facts now. First, for a simple graph, the matrix is symmetric. That means the entry in row I, column J equals the entry in row J, column I, and a simple graph has no loops, so every entry on the main diagonal is 0. Second, think about storage. If a graph has few edges, we call it sparse. Then the matrix is nearly all zeros, and a list saves a lot of space. If a graph has many edges, we call it dense, and a matrix is the better choice. A matrix can also hold loops and multiple edges. We just let the entries be counts instead of only 0 or 1. First rule. A loop at a vertex puts a 1 on the diagonal for that vertex. Second rule. When several edges join the same 2 vertices, the entry counts them. 2 edges give a 2. 3 edges give a 3. The matrix is still symmetric, but the numbers can now be larger than 1. Let's read this pseudograph into a matrix, row by row, using the order of B, C, D. Row A 3 lines join and in B, so the entry is 3. No line joins and in C, so 0. 2 lines join and in D, so 2. And no loop beta, so the diagonal is 0. The row is 0, 3, 0, 2. Row B back to a 3 again. 1 line to C, so 1. 1 line to D, so 1. The row is 3, 0, 1, 1. Row C nothing to A, so 0. 1 to B. Now the diagonal. There is 1 loop at C, so that entry is 1. And 2 lines to D, so 2. The row is 0, 1, 1, 2. Row D2 to A, 1 to B, 2 to C, and no loop, so 0. Now check the symmetry. Row A column B is 3, and row B column A is 3. The mirror still holds because the graph is undirected. We can also store a directed graph in a matrix. Here direction matters. The entry of sub ij is 1 when there is an edge that starts at vi and ends at vj. If there is no such edge, the entry is 0. Because direction matters, the matrix is usually not symmetric. There may be an arrow from vi to vj and nothing coming back, and then those two mirrored entries differ. For a directed multigraph, the entry simply counts how many arrows go from vi to vj. Now a third way to store a graph. It is the incidence matrix, and it is built differently. The rows stand for the vertices. The columns stand for the edges, so the grid has n rows and n columns. The entry is 1 when edge EJ touches vertex VI and 0 otherwise. Because rows are vertices and columns are edges, the grid is usually not square, and this is the useful habit. Read this matrix by columns, not by rows. Each column is one edge, and it tells you the two ends of that edge. Before we build the grid, let's read the ends of every edge straight off the picture. Edge E1 joins V1 and V4. Edge E2 joins V1 and V5. Edge E3 joins V2 and V4. Edge E4 joins V2 and V5. Edge E5 joins V3 and V5. And edge E6 joins V2 and V3. 5 vertices and 6 edges, so the matrix will have 5 rows and 6 columns. Now we fill in the grid, one vertex row at a time. The columns are the 6 edges in order. Row V1. Which edges touch V1, E1 and E2? So we put a 1 under E1 and a 1 under E2 and zeros everywhere else. Row V2. Edges E3, E4 and E6 touch it, 3 ones. Row V3. Edges E5 and E6, 2 ones. Row V4. Edges E1 and E3, 2 ones. Row V5. Edges E2, E4 and E5, 3 ones. Now check the work in 2 ways. Look down any column. It has exactly 2 ones because an ordinary edge has exactly 2 ends. And look across any row. The number of ones is the degree of that vertex. Row V2 has 3 ones, so V2 has degree 3. Now a harder one. Let's read what makes this graph different before we build anything. Step 1. Edge E1 is a loop at V1. A loop touches only one vertex, so its column will have a single one. Step 2. Edge E8 is a loop at V4. Same story. Step 3. Edges E2 and E3 both join V1 and V2. They are multiple edges, so those 2 columns will look identical. Step 4. In total there are 5 vertices and 8 edges, so the matrix is 5 by 8. Now we fill it in, 1 row at a time. The 8 columns are the 8 edges. Row V1. The loop E1 touches it, and so do A2 and E3, so one's under E1, E2, and E3. Row V2. Edges E2, E3, E4, E6, and E7 touch it, 5 ones. Row V3. Edges E4 and E5. Row V4. Edges E7 and E8, and E8 is its loop. Row V5. Edges E5 and E6. Now read the grid by columns and look for the 2 special shapes. Column E1 has only 1 entry, and so does column E8. That single one is the signature of a loop, and columns E2 and E3 are exactly the same. 2 identical columns are the signature of multiple edges. Now we ask a deep question. When are 2 graphs really the same graph? They may be drawn in different ways with different labels, but underneath they can have the very same shape. We say such graphs are isomorphic. This is the idea. We look for a matching between the vertices of the first graph and the vertices of the second graph. The matching must be 1 to 1 and onto, which means each vertex has exactly 1 partner and no vertex is left out. And the matching must keep the edges. 2 vertices are joined in the first graph exactly when their partners are joined in the second graph. Such a matching is called an isomorphism, and 2 simple graphs that are not isomorphic are called non-isomorphic. Two graphs here, G and H, we want to know whether they are isomorphic. We never guess. We compare invariants first, because an invariant that differs would settle the question straight away. Step 1, count the vertices. G has 4, H has 4. They agree, so it is still possible. Step 2, count the edges. 4 and 4 again, still possible. Step 3, write the degree sequences. In G, every vertex has degree 2, and in H, every vertex has degree 2. Both are 2, 2, 2, 2. Nothing has ruled it out. So now we must actually build a matching and check it. This is the matching we will test. F sends U1 to V1, U2 to V4, U3 to V3, and U4 to V2. Each U has exactly one partner, and every V is used once, so F is 1 to 1 and onto. Now push every edge of G through F and see whether it lands on an edge of H. Edge U1, U2 becomes V1, V4. Is that an edge of H? Yes. Edge U1, U3 becomes V1, V3. Yes. Edge U2, U4 becomes V4, V2. Yes. Edge U3, U4 becomes V3, V2. Yes. All 4 edges of G land on edges of H. G has 4 edges and so does H, so nothing is left over on either side. That is exactly what an isomorphism must do. So G and H are the same graph, just drawn differently. Deciding if two graphs are isomorphic is hard. Let's see why. Suppose each graph has n vertices. Then there are n factorial ways to match the vertices of one graph to the vertices of the other. For 10 vertices, that is already more than 3 million. Trying every match one by one is called brute force, and it is far too slow. Cleverer methods do much better than that. The fastest one we know runs in what is called quasi-polynomial time, which grows more slowly than an exponential. But it is still not a polynomial, so the problem is not known to be easy. But there is good news. Showing that two graphs are not isomorphic is often easy. We look for a property that every isomorphism must keep. Such a property is called a graph invariant. If one graph has the property and the other does not, they cannot be isomorphic. 3 simple invariants. First, the number of vertices. Second, the number of edges. Third, the degree sequence, which is the list of all vertex degrees written from largest to smallest. And remember which way this works. Different invariants prove not isomorphic. Matching invariants prove nothing on their own. 2 more graphs now. G and H, we want to know whether they are isomorphic. Each is drawn as a small square inside a big square, with 2 extra edges joining them. They look very much alike. Let's find out whether they really are the same graph. As always, we start by comparing invariants. Let's compare the invariants, one line at a time. Step 1, count vertices. 8 and 8, same. Step 2, count edges. 10 and 10, same. Step 3, find the vertices of degree 3. In G they are B, D, F, and H in H they are S, V, W, and Z4 in each graph. Step 4, find the vertices of degree 2. In G they are a C, E, and G and H they are T, U, X, and Y again 4 in each. So every easy test agrees. Be careful here. Agreeing invariants never prove that two graphs are isomorphic. They only mean the easy tests have failed to separate them. We need a sharper invariant. This is the sharper invariant. Take only the degree 3 vertices and keep only the edges that run between them. An isomorphism sends degree 3 vertices to degree 3 vertices, so it must carry one of these small graphs onto the other. Step 1. In G, the degree 3 vertices are B, D, F, and H, which edges run between them. Just B, F, and D, H, two separate edges and no cycle. Step 2. In H, the degree 3 vertices are S, V, W, and Z. The edges between them are SV, SW, WZ, and ZV, that is 4 edges, and they form a closed square. Step 3. Two separate edges in a 4 cycle are different shapes. One has 2 edges, the other has 4, so the invariant differs, and G and H are not isomorphic. There is a second way to reach the same verdict, and it is worth seeing. Step 1. In G, the vertex has degree 2. An isomorphism must send it to a vertex of degree 2. In H, the degree 2 vertices of H are T, U, X, and Y, so it must land on one of those 4. Step 2. Now look at those 4 in H. Take T, its neighbors are S of degree 3 and U of degree 2. So T has a degree 2 neighbor. Check U, X, and Y, and each one has a degree 2 neighbor as well. Step 3. Now look back at it in G, its neighbors are B and D, and both of those have degree 3, so it has no degree 2 neighbor at all. Step 4. Whether a vertex has a degree 2 neighbor is preserved by any isomorphism. Vertex does not have one, and every candidate partner does. So there is nowhere for it to go, and no isomorphism can exist. One last pair, and this time the answer will be yes. Again, we start with invariance. Step 1. Count. Both graphs have 6 vertices and 7 edges. Step 2. Find the degree 3 vertices. In G, they are U2 and U4. In H, they are V3 and V5, 2 in each. Step 3. The rest have degree 2. In G, that is U1, U3, U5, and U6. In H, it is V1, V2, V4, and V6, 4 in each. Everything agrees, so an isomorphism may exist. Now we go and build one. This is the matching. Notice how it was chosen. Each degree 3 vertex of G goes to a degree 3 vertex of H, and each degree 2 vertex goes to a degree 2 vertex. So U2 goes to V3, U4 goes to V5, and the other 4 fill in around them. Now push every edge of G through F. Edge U1, U2 becomes V6, V3. That is an edge of H. Edge U1, U4 becomes V6, V5. Yes. Edge U4, U3 becomes V5, V4. Yes. Edge U2, U3 becomes V3, V4. Yes. Edge U4, U5 becomes V5, V1. Yes. Edge U5, U6 becomes V1, V2. Yes. Edge U6, U2 becomes V2, V3. Yes. 7 edges in, 7 edges out, and H has exactly 7 edges, so nothing is missed. So F is an isomorphism, and the two graphs are the same. Now let's talk about the algorithms themselves. The best worst-case bound we know is quasi-polynomial. It was proved by Laszlo Babai in 2015, and it looks like e to the power of the logarithm of n that is far better than exponential, and still far worse than polynomial. In practice, things are much better again. On average, some algorithms run in linear time. There is also a free program called NAUTY. It can compare 2 graphs with up to 100 vertices in less than 1 second. And graph isomorphism holds a special place in computer science. It is one of the very few problems in the class NP that we cannot sort into either box. We do not know a fast polynomial time method for it, and we cannot prove it is NP complete either. Its status is still open. Why should we care about graph isomorphism? Because it shows up in real work. First, chemistry. A chemist can draw a molecule as a graph. Each atom is a vertex. Each chemical bond is an edge. When a new compound is made, its graph is compared to a big database of known compounds. If it is isomorphic to one already there, then it is not new. Second, electronic circuits. A circuit is also a graph. The components are vertices, and the wires are edges. Engineers check that the real chip layout matches the original design drawing, and they check whether one company has copied the protected design of another. We now begin section 10.4 on connectivity. It asks a simple question. Can we travel from one vertex to another along the edges of a graph? This is the plan for this section. First, we define paths. A path is a walk along the edges of a graph. Then we study connectedness in undirected graphs. A graph is connected if you can reach any vertex from any other. Vertex connectivity and edge connectivity are in the book, but not in these slides. After that, we look at connectedness in directed graphs, where edges have a direction. Paths and isomorphism are in the book only as well. And finally, we learn how to count the paths between two vertices. Let's begin with the idea of a path told in plain words. A path is a sequence of edges. It starts at one vertex, then it moves to a neighbor along an edge, then to another neighbor, and so on. As the path moves, it visits the vertices it passes through. Why do we care? Because many problems are really path problems. Can a message travel from one computer to another across a network? That asks whether a path exists. And how do we plan a good route for a mail carrier? That asks for a path that visits the right places. Now the exact definition. Let n be a whole number that is 0 or more. A path of length n from u to v is a list of n edges. E1 up to en along with them comes a list of vertices. x0 up to xn, here x0 is the start u, and xn is the end v. The rule is this. Edge ei joins vertex xi minus 1 to vertex xi, so the edges link the vertices in order. And look at the length. The length of a path is the number of edges, not the number of vertices. In a simple graph, the list of vertices alone names the path, because between two vertices there is at most one edge. 4 words to learn, and we will use all 4. First, circuit. A path is a circuit if it starts and ends at the same vertex, and its length is more than 0. So a circuit is a closed walk. Second, we say a path passes through its middle vertices. Third, we say it traverses its edges. And fourth, simple. A path or circuit is simple if it never uses the same edge twice. Read that carefully. The rule is about edges, not vertices. A simple path is allowed to come back to a vertex it has seen before, as long as it arrives on a new edge. Let's read this graph before we test any walk on it. Step 1, 6 dots A through F. Step 2, no arrows and no loops. Step 3, 10 lines. A B, B, C, a D, C, F, D, E, E, F, B, E, a E, C, D, and B, F. Step 4, and one fact we will need in a moment. Vertex E is joined to a B, D, and F it is not joined to C, remember that. Now we test 4 walks. The method is always the same. Take the vertices 2 at a time and ask whether that pair is really an edge. Walk 1, a D, C, F, E is a D an edge? Yes. Is DC an edge? Yes. Is CF an edge? Yes. Is FE an edge? Yes. 4 edges, none repeated, so it is a simple path of length 4. Walk 2, D, E, C, A is DE an edge? Yes. Is EC an edge? No, we saw that a moment ago. E is not joined to C. The walk breaks there, so this is not a path at all. Walk 3, B, C, F, E, B, B, C, yes, C, F, yes, F, E, yes, E, B, yes. 4 edges and it ends at B where it started, so it is a circuit of length 4. Walk 4, a B, E, D, a B, yes, B, E, yes, E, D, yes, D, a yes, and then a B again. 5 edges, so the length is 5, but the edge of B was used twice, so it is a path and it is not simple. Let's look at a friendship graph again. We call it an acquaintanceship graph. Each dot is a person. An edge joins 2 people who know each other. A path is then a chain of people, where each person in the chain knows the next one. One such chain runs Kamini, Jan, Paula, Todd, Kamlesh, Ching. Count the people and you get 6, but the degrees of separation count the edges, not the people. 6 people are joined by 5 edges, so Kamini and Ching are 5 degrees apart. This is the idea behind 6 degrees of separation. Many people believe that any 2 people in the world are joined by a path of at most 6 acquaintanceships. A famous play by John Gara takes its name from that idea. Another kind of graph now, a collaboration graph. Each dot is a person who has written a mathematics paper. An edge joins 2 people who wrote a paper together. Now pick the famous mathematician Paul Erdős. The Erdős number of a person is the length of the shortest path from that person to Erdős. If you wrote a paper with Erdős, your number is 1. If you did not, but you wrote with someone who did, your number is 2, and so on. You can look up your own number at the web address shown here. The table shows how many people have each Erdős number. Read it from the top left. Only one person has number 0, and that is Erdős himself. 504 people have number 1, so they wrote a paper directly with him. Then the numbers grow fast. About 6,500 at distance 2, about 33,000 at 3, about 83,000 at 4. The peak is at 5, with almost 88,000 people. After that, the numbers fall away again. Very few mathematicians are further than 8 steps from Erdős. Movies give us another graph. It is the Hollywood graph. Each dot is an actor. An edge joins 2 actors who appeared in the same movie. Now pick the well-known actor Kevin Bacon. The Bacon number of an actor is the length of the shortest path from that actor to Kevin Bacon. If you acted in a movie with Kevin Bacon, your number is 1. You can pick a different actor instead of Kevin Bacon and get a similar number. The Oracle of Bacon website works it out for you. These are the Bacon numbers. One person has number 0, and that is Kevin Bacon. 2,367 actors have number 1. And then look at number 3, 785,000 people. That is the peak, and it is enormous. Almost every working actor is within 3 or 4 steps of Kevin Bacon. Only 16 people are as far as 8, so the Hollywood graph is very tightly connected. Now we ask a simple question about a whole graph. Can we travel between any 2 vertices? If we always can, the graph is connected. If some pair has no path between them, the graph is disconnected. Notice how strong the definition is. It is not enough for most pairs to be joined. Every single pair must be. And when we remove edges or vertices and break a graph into pieces, we say we disconnect it. Let's test this graph. To show a graph is connected, we must find a path for every pair, so it is smart to try the pairs that look hardest first, the ones far apart. Step 1. From A to G go a then C, then F, then G. That works. Step 2. From B to E go B, C, D, E that works. Step 3. From G to E these two are at opposite corners. Go G, F, D, E that works too. Step 4. Every other pair is easier than these and each one has a path, so G1 is connected. Now the second graph, and here the answer is no. Step 1. Start at A and walk as far as you can. From A you reach B and C, and from those you reach nothing new. So the whole trip gives you only a B and C. Step 2. Now start at F. From F you reach D and E, and again nothing new. So you get only D, E, and F. Step 3. Is there any edge at all between the first set and the second set? Look carefully. There is none. Step 4. So there is no path from A to F1. Failing pair is enough. G2 is disconnected. Sometimes a graph is in several separate pieces. Each piece is called a connected component. A connected component is a piece that is connected, and that we cannot make any bigger by adding more of the graph. Look at the graph H. It falls into 3 pieces, and we have drawn each piece on its own. The first piece, H1, is a triangle with vertices of B and C. The second piece, H2, is a single edge between D and E. The third piece, H3, is a path through F, G, and H. None of these pieces touches another and none can grow. So H has 3 connected components. Now let's add directions to the edges. Here we have 2 kinds of connectedness. The first kind is strong. A directed graph is strongly connected when you can travel from any vertex to any other vertex, and back again, always following the arrows. The second kind is weak. First we rub out all the arrowheads. That gives an ordinary undirected graph, called the underlying graph. A directed graph is weakly connected when this underlying graph is connected. So strong is the harder test. Every strongly connected graph is also weakly connected, but not the other way round. Let's test this directed graph. Step 1. Start at A and follow the arrows. A to B, B to C, C to D, D to E, so from A we can reach every other vertex. Step 2. Can we come back to A? Yes, the arrow from E to A closes the ring. Step 3. Because those 5 vertices sit on one directed ring, the same trip works starting anywhere. From C, keep going around and you will pass through every vertex and return to C. Step 4. So there is a directed path both ways between every pair. The graph is strongly connected, and every strongly connected graph is weakly connected too, so that follows for free. Now the second directed graph. Step 1. Look at vertex A. How many arrows leave it? None. 2 arrows point into A, but nothing points out. Step 2. So we can never travel from A to B or to anywhere else. The test for strongly connected fails at once. Step 3. Now rub out the arrowheads and look again. As an undirected graph, this is one single piece. You can walk from any vertex to any other. Step 4. So the graph is weakly connected but not strongly connected. That is the difference between the 2 ideas in one picture. We can also break a directed graph into strong pieces. Each biggest strongly connected piece is called a strong component. Let's find them for the graph H we just saw. Step 1. Look at B, C, and D. The arrows B to C, C to D, and D to B form a directed ring. Inside that ring you can get from any one of the 3 to any other, so it is strongly connected, and it is our first component. Step 2. Vertex A, no arrow leaves A, so it can never get back into the ring. It cannot join any strongly connected piece, so A is a component all by itself. Step 3. Vertex E, we can reach E from D, but nothing leads out of E except the arrow to A, and from A there is no way back. So E is also alone. 3 strong components in all. Let's use these ideas on a huge real graph. The web. Each page is a vertex. Each link is a directed edge. A study from 1999 found the web had more than 200 million pages and more than 1.5 billion links. Today it is very much larger. Now apply our 2 tests. If we ignore the link directions, about 90% of the pages sit in one single connected piece. And if we keep the directions, there is one giant strongly connected component called the GSCC, with more than 53 million pages. Inside it, you can follow links from any page to any other page and come back again. Around that giant core, there are 3 more groups, and each one holds about 44 million pages. Group 1. Pages you can reach by following links out of the core, but which never link back in. Think of a page that everybody points to and which points nowhere useful. Group 2. Pages that link into the core but which you cannot get to from the core. A new blog that links to famous sites before anyone has linked to it. Group 3. Pages that cannot reach the core at all and cannot be reached from it. They sit off on their own. A clever result now. The adjacency matrix can count paths for us. The theorem says this. Take the adjacency matrix A, raise it to the power R, then the entry in row I and column J of A to the power R is the number of paths of length R from vertex I to vertex J. Notice how general it is. The edges may be directed or undirected. Multiple edges and loops are allowed. And notice what it gives us. A question about walking around a picture turns into a matrix multiplication, which a computer does very well. Let's see why the theorem is true. We use induction on R, the length. The basis is easy. When R is 1, a path of length 1 is a single edge, and the matrix accounts edges by its own definition, so the basis holds. Now the inductive step. Assume the entry Bij of A to the power R counts the paths of length R. Line 1. We want the Ij entry of A to the power R plus 1. Step 1. A to the R plus 1 equals A to the R times A, so by the rule for multiplying matrices, that entry is a sum of products. Bi1 times a 1j plus Bi2 times a 2j, and so on. Step 2. Now read each product. The first factor counts paths of length R from Vi to some middle vertex Vk. The second factor counts edges from Vk to Vj. Step 3. A path of length R plus 1 is exactly a path of length R to some middle vertex, followed by one more edge. The product rule counts those, and adding over every possible middle vertex gives them all. That is the entry we started with, so the step is proved. Let's use the theorem on a real example. The graph G has 4 vertices, B, C, and D, and 4 edges. We want the number of paths of length 4 from it to D. First, we need the adjacency matrix, using the order of B, C, D. Row A is joined to B and to C, so 0, 1, 1, 0. Row BB is joined to and to D, so 1, 0, 0, 1. Row CC is joined to and to D, so 1, 0, 0, 1. Row DD is joined to B and to C, so 0, 1, 1, 0. That is the matrix A. Now we raise it to the 4th power. This is a to the 4th power worked out. Line 1. We want the number of paths of length 4 from it to D. Step 1. The theorem says that number is the entry in row I, column J, where I is A and J is D, that is row 1, column 4. Step 2, read it off the grid. Row a column D, the entry is 8, so there are exactly 8 such paths. Look at the pattern in the matrix 2. The zeros are not an accident. In 4 steps from A you can only land on or D, never on B or C, because every step swaps you between the 2 sides. And these are the 8 paths in full, so you can check the matrix by hand. Each one starts at A, ends at D, and uses exactly 4 edges. The left column holds the 4 that leave A towards B, the right column holds the 4 that leave A towards C. Read the first one slowly. A B, D we go out to B, back to A, out to B again, and then down to D. That is allowed. A path may revisit a vertex. It only has to be a real sequence of edges. If we wanted simple paths which never repeat an edge, the count would be much smaller. Now we turn to a new topic, Euler graphs and Hamiltonian graphs. Can we draw a walk that uses every edge exactly once, or a walk that visits every vertex exactly once? These two questions look alike, but they turn out to be very different. This is the plan for this section. First, we study Euler paths and Euler circuits. These are about using every edge one time. Then Hamilton paths and Hamilton circuits. These are about visiting every vertex one time. At the end, we look at where Hamilton circuits are useful in real problems. Let's look at a famous old problem. It comes from the town of Königsberg in Prussia, which is now Kaliningrad in Russia. The river Pregel split the town into 4 regions. 7 bridges join those regions, and you can see them in the picture. People ask a simple question. Can you take a walk that crosses each bridge exactly once and comes back to where you started? For many years nobody could do it, and nobody could say why not. Leonhard Euler settled it, and his answer is often called the first theorem in all of graph theory. Euler's first move was to throw away the map and keep only the connections. Step 1. Each land region becomes a single dot. 4 regions, 4 vertices, A, B, C, and D. Step 2. Each bridge becomes an edge. 7 bridges, 7 edges. Step 3. Some pairs of regions are joined by 2 bridges, so 2 lines run between the same pair of dots. That makes the model a multigraph. Step 4. Now read the degrees. Vertex A has 5 lines, 2 to C, 2 to B, and 1 to D. Vertices B, C, and D each have 3. Check the total. 5 plus 3 plus 3 plus 3 is 14, and that is 2 times 7 edges, as it must be. First, we need 2 clear definitions. An Euler circuit is a closed walk. It uses every edge of the graph exactly once, and it starts and ends at the same vertex. An Euler path is almost the same. It also uses every edge exactly once, but it must start at one vertex and end at a different one. That last part matters. It is what keeps a circuit from also counting as a path. Remember the word simple here. It means no edge is repeated. And notice what is not being asked. We say nothing about visiting vertices once. A vertex may be passed through many times. It is the edges that must not repeat. Let's test the first graph. Step 1, count the edges. There are 6, a B, a E, EC, B, E, ED, and DC. Step 2, now the degrees. Vertex A touches B and E, so too. Vertex B touches A and E, so too. Vertex C touches E and D, so too. Vertex D touches E and C, so too. And vertex E touches a C, B, and D, so 4. Step 3, how many of those are odd? None. Every degree is even. Step 4. An Euler circuit needs exactly 0 odd degree vertices, and we have 0, so one exists. One of them is a E, C, D, E, B, A follow it. 6 steps, 6 different edges, and we finish back at A. Notice that we pass through E twice, which is allowed because we arrive on a new edge each time. Now the second graph, which is a square with a hub in the middle. Step 1. Count the edges, 4 around the square and 4 spokes, 8 in all. Step 2. The degrees. Vertex touches B, D, and E, so 3. The same for B, C, and D, and the hub E touches all 4 corners, so 4. Step 3. How many odd degrees? 4 of them, a B, C, and D. Step 4. Now name the criterion. An Euler circuit needs 0 odd degree vertices. An Euler path needs exactly 2. We have 4, so neither one exists, not a circuit and not even a path. Now the third graph. Step 1. Count the edges. A B, a C, a D, B, D, C, D, D, E, and B, E, 7. Step 2. The degrees. A touches B, C, and D, so 3. B touches a D and E, so 3. C touches A and D, so 2. D touches a B, C, and E, so 4. And E touches D and B, so 2. Step 3, which are odd, just and be exactly 2 of them. Step 4, now name the criterion again. 0 odd vertices would give a circuit, and we do not have that. Exactly 2 odd vertices gives a path, and that is what we have. So there is an Euler path, and it must start at one odd vertex and end at the other. One of them is a C, D, E, B, D. A B, it uses all 7 edges once, and it runs from it to B exactly as promised. Let's see why the degrees must come out even. Think about an Euler circuit. It starts at a vertex A. The very first step leaves along one edge, and that uses one edge end at A. Now think about any other vertex on the way. Each time the walk reaches it, the walk comes in on one edge and goes out on another. So it uses 2 edge ends per visit, and 2 is even. Finally, the walk comes back to and stops, using one more end at A. So I got one at the start and one at the end, which is 2. Every vertex ends up even. For an Euler path, the start and the end are different vertices, so each of those gets an odd count, and all the others stay even. Now we show the other direction. Even degrees are not just necessary, they are enough. Take a connected graph where every vertex has even degree. Start anywhere, say at A, walk along edges, one after another, never repeating an edge, and keep going until you cannot add a new edge. This is the key point. Every time you arrive at a vertex that is not a, count the edge ends you have used there. Each earlier visit used 2, one to come in and one to go out. This arrival uses one more, so the used count is odd. The degree is even, and an even number minus an odd number is odd, so at least one end is still free. There is always another unused edge to leave by, so you can never get stuck in the middle. You can only get stuck back at A, which means the walk closes into a circuit. In our picture, start at O and take it to F, F to C, C to B, and B back to A. Now the edges among C, D, and E are still unused. Let's finish the argument. The graph G is connected, so the leftover graph H must touch our first circuit at some shared vertex. Also, every vertex in H still has an even degree, because at each vertex we removed edges 2 at a time, one in and one out. So we can play the same game inside H, start at the shared vertex, build a second circuit, and then splice it into the first one at that vertex. Repeat, and each round uses more edges. In the end, every edge is used exactly once, and that is an Euler circuit. In our example, the shared vertex is C, and the triangle CDE is the leftover. Splice it in and we get a FCDECBA. And the same idea works for a path, if there are exactly two odd vertices. This is the method written as an algorithm. We give it a connected graph where every vertex has an even degree. First, we build one circuit. We start at any vertex and add edges until we come back to that vertex. Then we make H, which is the graph with those used edges taken away. Now we loop. While H still has edges, we find a vertex V that is in H and also lies on our circuit. We build a small circuit from V, which we call sub. We remove its edges from H, and we remove any vertex left with no edges. Then we splice sub into our main circuit at V when H has no edges left. We stop, and the circuit we are holding is a full Euler circuit. Now we can state the full theorem, and it is an if and only if, which is the strongest kind. Take a connected multigraph with at least two vertices. It has an Euler circuit exactly when every vertex has an even degree, and it has an Euler path exactly when it has exactly two vertices of odd degree. This is a wonderful test. You do not have to search for the walk. You just count degrees and the count tells you the answer. Let's settle the Königsberg question. Step 1. List the degrees from our multigraph. A has degree 5. B, C, and D each have degree 3. Step 2. How many of those are odd? 5 is odd and 3 is odd, so all 4 vertices are odd. Step 3. Now name the criterion. An Euler circuit needs 0 vertices of odd degree. We have 4, so there is no Euler circuit. Step 4. And an Euler path needs exactly 2. We have 4, so there is no Euler path either. That settles it completely. The famous walk is not just difficult, it cannot be done, and now we know exactly why. Let's practice the theorem on 3 graphs. This is the first. Step 1. Count the edges, a B, B, C, C, D, a D, and B, D, 5. Step 2. The degrees. A touches B and D, so 2. B touches a C and D, so 3. C touches B and D, so 2. D touches C and B, so 3. Step 3. The odd ones are B and D, exactly 2 of them. Step 4. Exactly 2 odd vertices means an Euler path exists, and it must run between those 2. One of them is D, a B, C, D. B 5 steps for 5 edges, starting at D and ending at B. Now the second graph, which is bigger. Step 1. Count the edges. There are 11. Step 2. The degrees first half. Vertex A touches G and B, so 2. Vertex B touches C and G, so 3. Vertex C touches B, D, G, and F, so 4. Vertex D touches C, F, and E, so 3. Step 3. The rest. Vertex E touches F and D, so 2. Vertex F touches G, E, C, and D, so 4. And vertex G touches a F, B, and C, so 4. Step 4. So exactly 2 vertices are odd, B and D, that gives an Euler path from B to D. One of them is B, a G, F, E, D, C, G, B, C, F. D follow it slowly, and you will see all 11 edges used once each. Now the third graph. It is a wheel with 6 rim vertices. Step 1. Count the edges, 6 around the rim and 6 spokes to the hub, 12 in all. Step 2. Take any rim vertex. It has 2 neighbors on the rim plus the hub in the middle, so its degree is 3. Step 3. That is true for all 6 rim vertices, a through F, so 6 vertices have odd degree. The hub G has degree 6, which is even. Step 4. Now name the criterion. We need 0 odd vertices for a circuit, or exactly 2 for a path. 6 is neither, so this graph has no Euler circuit and no Euler path at all. Let's see where Euler paths and circuits are useful. An Euler path uses every edge one time, so it fits any job that must cover every connection once, and no more than once. For example, we may want to drive down every street in a neighborhood, or along every road in a transport network, or check every connection in a power grid, or test every link in a communications network. There are other uses too. Engineers use them when they lay out circuits. Networks use them to send one message to many computers, and biologists use them to read the order of DNA. An Euler path used every edge one time. Now we change the rule. The change is small, but the effect is enormous. We want a path that visits every vertex one time. This idea comes from William Hamilton. In 1857, he made a puzzle called the Icosian Puzzle. It used a wooden solid with 12 flat pentagon faces, called a dodecahedron. At each corner there was a peg, and each peg carried the name of a city. The player used a string to make a route that visited all 20 cities once and returned to the start. That is William Rowan Hamilton, who lived from 1805 to 1865. This is the puzzle itself. Picture A shows the wooden solid, and picture B shows the same puzzle flattened out into a graph. The 20 corners become 20 dots, and the edges of the solid become the edges of the graph. And this is one solution. The blue line is a route that touches every vertex exactly once, and then comes back to where it began. We call such a route a Hamilton circuit. Now let's write the two names clearly. Take a simple path in a graph G. If this path visits every vertex exactly once, we call it a Hamilton path. Take a simple circuit, which starts and ends at the same vertex. If it visits every vertex exactly once, we call it a Hamilton circuit. The formula says the same thing in symbols, and it says it in two parts. First, the set V is exactly the list of vertices on the path, so nobody is left out. Second, xi is never equal to xj for different I and j, so nobody is used twice. Together, those two conditions say every vertex exactly once. 3 small graphs to test. For each we ask, is there a Hamilton circuit? If not, is there at least a Hamilton path? Step 1, read this one. 5 vertices and 5 edges. Step 2, every vertex has degree 2, so the graph is just the cycle C5. Step 3, walk right around the ring. A, then B, then C, then D, then E, and back to A. Step 4, that visits all 5 vertices exactly once, and it returns to the start. So it is a Hamilton circuit. Any cycle Cn gives 1 for free. Now the second graph, and this is where the criterion matters. Step 1, the degrees. Vertex A touches only B, so its degree is 1. Vertex B touches A, C, and D, so 3. Vertices C and D each have degree 2. Step 2, now think about what a Hamilton circuit must do at every vertex. It arrives on one edge and leaves on a different one, so every vertex needs at least 2 edges. Step 3, but it has only one edge, so a Hamilton circuit cannot exist. That is the reason, and it is worth stating rather than just saying no. Step 4, a path is different. A path has 2 ends and an end vertex is only entered, never left. So a may be an end. Try a B, C, D all 4 vertices each once. That is a Hamilton path. Now the third graph, where both answers are no, and we can say exactly why. Step 1. The degrees. Vertex A has one edge, to be vertex E has one edge, also to be vertex B has 4. Vertices C and D have 2 each. Step 2. A vertex of degree 1 cannot lie on any circuit because a circuit must both enter and leave, so there is no Hamilton circuit. Step 3. Now try a path. A path has exactly 2 ends. A degree 1 vertex can only be an end. We have 2 of them, O and E, so they must be the 2 ends, and the path must run from A to E. Step 4. But the only edge at A goes to B, and the only edge at E also goes to B, so the path would have to pass through B twice, once on the way out of A and once on the way into E. A Hamilton path may not repeat a vertex, so no Hamilton path exists either. For Euler circuits, we had a clean test that worked both ways. For Hamilton circuits, we do not. Nobody knows a simple condition that is both necessary and sufficient, but we do know some helpful rules that guarantee a circuit exists. The first is Dirac's theorem. Take a simple graph with n vertices, where n is at least 3. If every vertex has degree at least n over 2, then the graph has a Hamilton circuit. The second is Orr's theorem. Again, a simple graph with n vertices and at least 3. Pick any 2 vertices u and v that are not joined by an edge. If the degree of u plus the degree of v is at least n, and that holds for every such pair, then the graph has a Hamilton circuit. Both rules give a guarantee one way only. If the rule fails, the graph may still have a Hamilton circuit. These are the 2 mathematicians behind those theorems. First, Gabriel Andrew Dirac, who worked in Britain and Denmark, and Øystein Orr, a Norwegian mathematician who spent most of his career at Yale. Orr's condition is the more general of the 2. If every degree is at least n over 2, then any 2 degrees add to at least n, so Dirac's condition always implies Orr's. Where do Hamilton paths help us? Think of a job that must visit every point exactly one time. For example, visit every road intersection in a city, or every place where pipelines meet in a grid, or every node in a network. Each of these is a Hamilton path problem. One very famous case is the traveling salesperson problem, or TSP for short. A salesperson must visit a set of cities and come home. We want the shortest total route. That is the same as finding a Hamilton circuit whose edge weights add up to the smallest value. And one more nice use. A gray code is a way to list binary codes so that only one bit changes at each step. That helps reduce errors. Such a code is exactly a Hamilton circuit in the n cube Qn, because in the n cube an edge is a 1-bit change.